Alright guys, welcome to Chapter 7. Here we start learning the foundations of inference. That is, we start learning why we are able to make accurate and trustworthy conclusions from just a sample from our population. This is where things start to get abstract and difficult for some, but if you pay attention to the language we use, you'll be okay. So make sure you have your EQ down and your assignment written. Pause if you need to, and let's get going. Alright, so the major goal of statistics is to make an inference about a population. The whole idea is to take information from a small subgroup of a population to say something about everybody in the population. But because we randomly sample from that population, we sometimes get individuals that are unusual, right? Or we call these guys the outliers. Now, these can make our inferences or conclusions sometimes incorrect. That's okay. What we can say is that by using the proper methods of collecting information, like through random sampling, usually we are going to come up with an accurate description of the population. But why can we say this? Well, sampling distributions demonstrate how this actually works. And by examining sampling distributions, we finally get to see why random samples can generally speak for everybody in a population. Now, before we can start looking at sampling distributions, we need to examine the difference between the information we want to know versus the information we actually collect. So first there is the parameter, okay? This is usually the information we want to know, the information that is true about an entire population. So we define a parameter as a number that describes some characteristic of the entire population, like an average or a median, IQR, etc. But then there's a statistic. Okay? A statistic is a number that describes some characteristic of a sample of that population. These can also be averages, medians, IQRs, etc. So what's the difference? Well, let's say I want to know the average height of a 17-year-old at Spring Valley. If I measured every 17-year-old in the school and recorded their height, I could calculate the average height to be mu equals 5 feet 7 inches, right? Now, this would be from a census, and so that means I know that this is true for the entire population because I conducted a census. But that's way too much work. So instead, I measure everyone in my classroom that is 17 and calculate that average. Now, this isn't the population average, it's the sample average height, which we call X bar. Let's say that this X bar happened to be 5 foot 8 inches. That would be my statistic. It came from a sample. Now, this statistic might be a little bit off from the true mean height, but it's generally pretty close. It's less work and usually gives me a reasonable guess. The other thing that we have to understand about parameters is that we usually don't know for sure what the value is. It's simply a claim. Somebody tells you that the average height of students is 5 feet 7 inches. And a lot of times we want to generate evidence that will support or refute that claim. We get a statistic to actually do that. So now that we understand the difference between the parameter and statistic, we want to notice the difference in notation. Remember, communication is key in statistics, and here we had two different symbols for mean. So we want to make sure that we are using the right ones when we're talking. We saw that mu is the population for the parameter, the Greek letter mu. And I'll go ahead and write this in here that that's our population, right? So the population mean, we would call that mu. X bar, however, was the sample mean or the statistic. So statistics come from samples and parameters come from measuring the entire population, okay? Now, the other two most commonly used parameters and statistics we will discuss are the standard deviation and the proportion, or what we know as percentages. So don't get freaked out by that word proportion. You know what we're talking about. The population standard deviation, we use the lowercase sigma, another Greek letter. And then the sample standard deviation, we've used this symbol before, S sub x. The population proportion, or percentage, we use a lowercase p in most cases and textbooks. And for the purposes of the AP test and our class, we will use this lowercase p right here, okay? But some texts will use the Greek letter pi, okay? The sample proportion, however, is the lowercase p, but with a hat. Kind of like what we did in linear regression, we had y hat. That was used to make a prediction. P hat is a proportion that comes from sample measurements. So Except for that weird lowercase p, there's a general rule of thumb that parameters, or things that describe the population, are going to use Greek letters or symbols. Okay, so when we're talking about the population mean, we're going to use mu. Population standard deviation, we use sigma. English letters, however, are going to always be used, for the most part, I should say, to talk about statistics or things that come from samples. Understanding the difference in notation is going to be key for you reading and communicating in this chapter and beyond. So now, please check out examples 1 and 2 and see how you can tell the difference between parameters and statistics and use the proper notation too. Alright, so for example 1, we want to identify the population, the parameter, the sample, and the statistic for each of these. So here we have a pediatrician. She wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So that right there, that tells me what the population is and actually what she wants to know. That's my parameter. So we start off with our population is all 10-year-old boys. And then we have our parameter, in this case, was the 75th percentile of the population. So, 75th percentile of heights of 10-year-old boys. Okay. Next, we continue reading. So she takes a sample of 50 patients and calculates that the 75th percentile in sample is 56 inches. So that makes it really easy. We've got our sample. We know that was 50 of her patients. Okay, and then we have our statistic, what she actually measured from each of these. So the important thing, this one was really easy, that it was all spelled out for us and even in order of what we wanted to know. 56 inches, that was the 75th percentile of the sample. So not always are we going to see this where it's that easy for us. You're going to have to read into it a little bit more usually to find out what our sample is and what our statistic is, but this one was pretty straightforward. You guys go ahead and do part B of number 1. And go ahead and we'll take a look at example number 2. Alright, so for example number 2, each boldface number is going to be either a parameter or a statistic, and in each case we want to state which it is and use appropriate notation to describe the number. So here we have on Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. So that is our first boldface number, and since this is talking about all of the bottles that were produced in the plant on that day, 20 would be considered my parameter. Okay, and now that says on average, so we would say mu equals 20, right? Mu is the notation we're going to use for a population mean. Now, quality control inspector sampled 50 bottles at random from the day's production. These bottles contain an average of 19.6 ounces. So we have another average, but this time 19.6, we are going to call that our statistic because it came from a sample of 50 bottles only, not the entire population. And when something's coming from not the entire population, we have 19.6 ounces. This was also in ounces. And there we have it. Okay, so go ahead and try the second part of example 2. Identify which one is the mu and which one's the x bar or the p or the p hat, whatever population parameter and statistic you are looking for. Okay, so now that we can tell the difference between parameters and statistics, let's actually take a look at the sampling distribution. This applet that I have here on my screen is going to help us simulate taking a bunch of random samples from a population and record a sample statistic, namely, this time, the mean of a sample. So let's imagine this distribution you see at the top is a population of scores for students that they took on a recent test out of 32 points. Okay, we see the typical score was here somewhere in the middle, and then we had some students do really well, we had some students do not so well, and then we've got some gaps over here in the middle. Okay, now let's say that these were my students, and I have to report how well my students did on this test to my boss, but I don't have time or the access to the whole population to calculate the entire population average. What I can do is take a sample of 5 students' tests and calculate the average for me to report. That's a lot easier. So let's do that. So I'm going to go and click this animated button, and that's going to show these 5 black blocks dropping down representing a sample of 5 students. And now you'll notice that a blue block fell from that. That represents my sample average. So this first graph here is what we call a distribution of sample data, which is what you've been doing whenever you've collected data all year long. You just never had a name for it. It's a distribution of the values taken by a sample you select from a population. Now, my question is, was this particular sample reliable? Was this really representative of my whole population? Well, if you look here, we can see I actually do have the population mean up here in the top left, and it says that the average score on this test was 21.68. We had a standard deviation of 5.77, and that is displayed right here in this darker blue. It looks like the average I had was, hey, right on the money. That's pretty good, okay? But let's take another sample to see what a different average from 5 different students looks like. Notice that, wow, we had 4 students that were all near the top, right? All above average, and then we had one that was almost all the way at the bottom, and that gave us a sample that was a little bit higher than average. So in that case, if this happened to be my random sample of 5 students, I would actually be overestimating that average a little bit, and that might not look so great for me. Let's take a look at another sample of 5 and see what happens. There it's even higher than what I had. This is even seemingly more reliable. It's less variability, but I still get a very high sample average. Let's take a look at another 5 individuals from my distribution of sample data, and now I get one that's below average. Okay, so if we do this again, and again, and again, and we do this many, many times, I want to see a bunch of samples of 5 students. I want to know what that looks like, and I want to calculate the average. Well, why do I want to do that? Why is 1 not good enough for me, right? Well, what I want to know is if I am taking this random sample, how likely am I going to get an average that is representative of my sample? Or am I likely to generate a sample that's overestimating, like I had one over here, or underestimating, like I had one over here, that's underestimating my students' test scores? Either way, it's disingenuous, and it doesn't look good for me. It looks like I'm lying. I want my sample to reflect the true mean of the population. So instead of doing this one sample of 5 students at a time, I'm now going to take a look at thousands of samples at a time, each time generating a new average. The blue blocks would keep dropping, doing this over and over again, and each blue block represents a new sample average from a different combination of 5 students and their test scores. So let's take a look at what sampling 10,000 samples of 5 students would look like. Boom. Here, we now have this distribution of a whole bunch of sample means. You see it right here in the name, distribution of means when n, my sample, equals 5. And you'll notice that I even have an average here. Well, let's do this another 10,000 times, see what happens. Shape doesn't change that much. Another 10,000, or maybe 100,000, 100,000, another 100,000. We keep going, and maybe just one more for good measure. I'm up to now 430,000 samples of 5 students' combinations of test scores, and I've taken the average of those. So, notice the mean now, this blue block's distribution, 21.68. It's exactly the same as the population distribution. So what does the blue block mean actually tell us? What is this 21.68 that's down here? Well, again, if you look at the name of this graph, it says it's a distribution of means. Specifically, it's the distribution of sample means when we look at 5 randomly selected students. This is what we call a sampling distribution. It's a distribution of values taken by the statistic in all possible samples of the same size from the same population. The statistic we used was X bar. So what this sampling distribution tells us is that the typical average we will get from a sample of 5 students is 21.68. And what's really important here is that the average of the sampling distribution is exactly the same as the value of the average of the population, which means typically when I draw a sample of 5 students, like I do here, and I get a new mean, it's going to not be close, but exactly the same. When I do this over and over and over again, it's going to be exactly the same as the population average. So I get a sample average that is not close to the population average, but exactly equal to the population average. Now, let's reiterate this by looking at example number 3. So this example will show us again why we care about the sampling distribution. We touched on it a bit in that last applet, but I want to reiterate it now. So imagine we have a population of random numbers. In this case, they happen to be 3, 4, 6, and 7. And let's say I am curious about the population median. Well, that's easy enough for us to calculate. The middle two numbers are 4 and 6. Halfway in between those is 5, right? Okay, but what if I'm taking random samples of size n equals 2 from this population? Well, there are exactly 6 random samples that we can take. So let's go ahead and look at the possibilities. The first possibility I have is 3 and 4. And now I'm going to, so this is a sample of 2 numbers at random, and I'm going to say the median of these two is halfway between 3 and 4, and that's 3.5. Okay. The next possible sample I have is 3 and 6. So if we look at 3 and 6, the median of those two is going to be 4.5. The next sample I have is 3 and 7. And the median of those two numbers is 5. Okay, now I've done all the samples I can with 3. Let's go ahead and move on to 4. I can have 4 and 6, and the median of those two numbers is just like the last one, it's 5. Then we have 4 and 7. Median between those two numbers will be 5.5. And then the final one we have is 6 and 7. And the median between those is going to be 6.5. Okay. Now we can do what's called creating a sampling distribution. Since the sampling distribution is a distribution of all values of a statistic, in this case the sample median, of all possible samples of the same size from the same population, I'm going to plot each of these sample medians that we found. 3.5, 4.5, 5, and 5.6, and 6.5. Okay? Now, I'm not going to use dots in this dot plot that I have down here. I'm actually going to use capital M's because I want to make very clear that these are not individuals, but these are in fact medians from samples of size 2. Okay, the first one we had was a median at 3.5. Then I had one at 4.5. I had 2 occurring at 5. We have one occurring at 5.5. Oops. Pretend that's a good looking M, sorry, and then 6.5. Okay, now my question for you is, what would you say is the average of all of these sample medians? Guessed it, it's the one that's right in the middle. The average of this distribution of all of these sample medians is indeed 5. Okay, and this we would actually call the mu of the medians. And the mu of all those medians is equal to 5, and if you remember, this happens to be exactly the same as the population median. They are identical. So, the conclusion we can draw from this abstract idea is this: the fact that the average of all possible samples of a statistic, in this case medians, might actually equal the parameter, in this case the population median, tells us that samples we take are generally reliable enough to tell us some truth about the population. So this tells me, hey, you know what, even though there's some sampling variability, we are generally, on average, going to get the exact same median as we would if we looked at the population median. Okay? So, that's the importance of sampling distributions. Now it's going to lay a foundation for everything else we do for the rest of this chapter. Alright, so this is all well and good, but we still have this problem, namely sampling variability. Each distribution of sample data is likely going to be different. We're going to have different x-bars, different s sub x's, IQRs, medians, and etc. But the idea behind taking a sample of a population is to be able to say something about the population as a whole. So how can we be certain that our calculations from the sample is indeed trustworthy enough to say something about the whole population? We saw this work for means and medians through the sampling distribution, but will it work for any statistic? And will it work for all means and medians we examine? So, to do that, we usually have to examine and describe key components of sampling distributions before we can learn to trust any random sample. So, let's think back. Chapter 1, how have we described distributions before? You guessed it, we look at the SOCs, right? Now, instead of starting with shape and going into outliers, I want to focus next on spread. I want to focus on center. So we usually have to examine and describe key components of sampling distributions before we can trust a sample. So how have we described, 3, 2, 1. Now we usually have to describe 3, 2, 1. We usually have to examine and describe key components of sampling distributions before we can trust a sample. So how have we described distributions before? Well, you guessed it, we're going to use SOCs. Right? But instead of going through shape and outliers, I actually want to jump right into center. So let's start by describing sampling distributions and their centers. So looking at spread, here we see two different sampling distributions of a sample proportion or a percentage. Okay? These are coming from the same population, but there are two key differences between the two. First, I want you to notice the sample size of each. Here we have n equals 100 and another n equals 1000. So this one on top with n equals 100, compare that to the sampling distribution where n equals 1000. Here we took a bunch of samples of size 100, and you'll notice that it's considerably more variable, right? There's a lot more spread to it than if we were to take every time looking at samples of 1000 and calculating a proportion from each of those samples. Okay, so the second distribution, being considerably less variable, means that each sample in this distribution, when we take 1000 individuals in our sample every time, is going to be a much more reliable estimate of the population proportion. The closer my sample proportion is to the thing I'm trying to estimate, the population proportion, the better. Also, notice that the center of the second distribution is a lot more obvious. It's a very, very clear peak. It's very tall, and most of the dots are all very close to it. So it's clear what the true population proportion should be. This brings us to an important conclusion about variability of sampling distributions. So, first of all, the variability of a statistic is described by the spread of the sampling distribution. And what we are going to find here is that low variability in a sampling distribution is better. Always. The lower the variability of the sampling distribution, the more likely I am to have a sample that accurately estimates the parameter. Well, how do we get lower variability? By taking larger samples. Okay? Larger samples will always give you smaller spreads. So, two things to evaluate from a sampling distribution. First of all, the center of a sampling distribution must be the same as the parameter. That makes it unbiased. So, center of the sampling distribution must be the same as the parameter. Second, we want to make sure that there is low variability in the sampling distribution. If these two criteria are met, then we should have a very trustworthy sample from the population. Any one of our samples should be fairly trustworthy. So finally, we're going to wrap this up, first section of Chapter 7. I know it was long and very wordy. I apologize. There's no other way around it. With an example that puts everything together in context. So please take a look at example 4, and we'll do that one together. Okay, for this example, we're going to suppose we read an article that suggests the average adult male is 70 inches tall, and they happen to follow a normal distribution with a standard deviation of 3 inches. But you are skeptical of this, and you want to conduct 2 different statistical studies to test it out. You use statistical software to simulate many random samples, and in this simulation you took 200 simple random samples of size 100, calculated the sample mean height, and then took 200 simple random samples of size 1500 and calculated their sample mean height. So let's take a look at these graphs and compare them. So A, what conclusion can you draw from these about the relationship between sample size and the variability of the sample means? Well, we take a look at the first one on the left, and that has a sample size n equals 100. The other one much larger, and the big thing that we just talked about was, hey, they are a considerably different variability. So sample size 100 has a significantly larger variability. We don't want large variability, we want small variability. It means more reliability. So when we have a larger sample size, the sampling variability, that means that the variability in the sampling distribution goes down dramatically. Okay. Next, we are going to look at this one here, part B. There's a dot on the left dot plot at about 69.1, so that's right here. What does this dot represent? Well, remember, this is supposed to be a simulation of a sampling distribution. So this isn't actually an individual at 69.1 inches. This is representing a sample that was taken, had a average height of 69.1 inches. Not an individual, but this was a sample of 100 males, calculated average of 69.1 inches. And I should actually also indicate here that this was a sample of 100 adult males was taken, and an average height calculated of 69.1 inches. Next, we want to look at part C. Suppose that you actually measure a sample of 100 adult males. So now we're throwing out the idea of a simulation. You're actually going out and collecting this information. You get an average height of 69.7 inches. Does your sample suggest that the true average height viewed does not equal 70 inches? Explain. So here's 69.7 inches right here on the graph. What we're trying to pay attention to is how likely was this to have happened? Well, it looks like there are about 10 to 20% of all of those dots, of all samples, had something 69.7 inches or less. So, since I had about 10 to 20% of simulated samples with average heights less than or equal to 69.7 inches, this is unlikely, but not surprising. Since the outcome is not terribly surprising, I wouldn't say that that gives me evidence against the claim. It doesn't refute it. I'm looking for something that is so unlikely it couldn't have happened by chance alone. We must have a fault with our claim. So, since the outcome is not terribly surprising, I do not have very convincing evidence to refute the claim. Next, we will take a look at D. So now we are going to suppose that we actually took a sample of 100 adult males again, but now the average height is 71 inches instead of 69.7. So now that's interesting, because if we look over here at this same one where we took all of our samples, did we have any samples where we had 71 inch high averages? No. In fact, we didn't have any that were even really close. 70.6 inches was the next smallest. So since my simulation indicates that a 71 inch average of 100 adult males is extremely unlikely. In fact, based on the simulation, this was impossible, right? We didn't even get a simulated sample where we had something that was 71 inches. I would say that this gives us actually very convincing evidence that we can refute the claim. Since our actual sample was so unlike what our simulation was, it suggests that there might be something wrong with the claim to begin with. Okay, so that's everything we've got for today with section 7.1. I know it was long and very wordy. No really other way around it. I have for you guys a an exercise again where you get to kind of play around with your own sampling distributions and go through this whole thing again. So please get working on that. You can take a look at your homework. Have a wonderful day, and I will see you guys when we take a look at 7.2.